Hi, welcome back. What we're going to do in this video is we're going to talk a little bit about Schiff-based chemistry. So Schiff-based chemistry is very important in organic synthesis. It's a handy tool, but also when you get into biochemistry, there's a lot of enzymes that tend to use Schiff-based chemistry. One of the ones that we looked at in glycolysis is aldolase. So aldolases use one form of Schiff-based chemistry. Another one that tends to use it are monoamine oxidases. Okay, the mechanism of the Schiff-based formation is different in each case, but the point is they both form Schiff bases, and then there's a subsequent Schiff-based hydrolysis in which the mechanism is identical. Okay, now this man who's shown on the left here, his name is Hugo Schiff. He was a German chemist who really started the whole movement in terms of Schiff-based chemistry. But the point is that Schiff bases are a very, very handy tool, and the reason that one of the effects of them being such a handy tool is that the cell utilizes Schiff-based chemistry to a very large extent. Okay, now the first thing we need to do is get some terminology straight. Okay, so when I draw nitrogen with 3 bonds, okay, it doesn't matter what the groups are, right? It has a lone pair on it, right? What would you call this molecule? Well, in general, we would call it an amine, right? This is just an amine, okay? Now, what happens if, say, you have the nitrogen, but it has 4 single bonds? What happens? So the terminology that you would call this would be an aminium, right? Aminium, right? So the actual nature of the fourth electron domain, whether it's a lone pair or it's a bond, dictates what the terminology is for this particular functional group, right? So in the case of something like acetylcholine, so here's the structure of acetylcholine. This nitrogen has a plus charge, and by the way, I can't forget the plus charge here. The nitrogen of the choline group of acetylcholine would be an aminium. Okay, we don't call it an amine, and the reason we don't is because it has 4 bonds attached to it. Okay, and again, the aminium that I've drawn here along with the amine, it doesn't matter what the groups are attached to it. Now, there's another type of nitrogen-containing compound. This one's a little bit different, though. Okay, essentially what you have is you have a nitrogen that has a lone pair. It has 1 single bond, which really could be to anything. It could be, generally we're just talking about a carbon or a hydrogen, and then there's some R group over here that has a double bond to the nitrogen. Okay, this particular molecule, the functional name of it is called an imine. Now what I want you to notice is that this is an I. This is not an A. So when you have a nitrogen that is singly bonded to some group, usually a carbon or a hydrogen, and it's doubly bound to usually a carbon, and it has a lone pair, we call it an imine. And so by this logic, you could imagine what we would call something like this, where you have a positive charge on the nitrogen. This would be called an aminium. Now, one thing that makes this difficult nomenclature is when you say amine or say imine, you tend to a lot of times not be able to tell what the person's talking about because they sound very, very similar. Okay, so because of that, and by the way, these particular compounds right here were discovered by Hugo Schiff. Okay, he's the one that started the whole movement on Schiff-based chemistry. So for that reason, we call the imine, we call it a Schiff base. Okay, and the reason it's called a base is because the nitrogen there can act as a Lewis base, whether it's abstracting a proton or acting as a nucleophile. Okay, so we call it a Schiff base. And so what we call the iminium is we call it a protonated. Usually, and this is usually the case if you have a proton here, you call it a protonated Schiff base. Okay, so in the context of biochemistry for these videos, you will, unless it's a slip of the tongue, you will never hear me say imine. You will hear me say Schiff base, and the reason we do that typically is because amine sounds like imine. And so when you hear me say amine, I'm talking about nitrogen with 3 single bonds. Okay, when I say Schiff base, I'm of course referring to nitrogen with a double bond. Okay, now Schiff-based chemistry, like I said, is very it has high utility, and it's very, very interesting. Now, in this video, what I want to do is explore one method of Schiff base formation and the mechanism of Schiff base hydrolysis. Now, the mechanism that we're going to look at for the formation here is actually the mechanism that's utilized in the mechanism of aldolase, which is, recall, your fourth glycolytic enzyme. Okay, so basically, when you form a Schiff base in a method like this, what you're assuming is that you're starting with an aldehyde or a ketone. Okay, generally with these Schiff base formations, you're starting with one of those. Okay, so we're not going to look at the mechanism per se of aldolase here, but let's just say I have a ketone. Okay, so I have a ketone, just a generic 2-propanone, right? Now, the first step of any Schiff base hydrolysis, okay? Now, let's assume that there's an R group here. Okay, let's assume there's an R group, and this is going to be NH2, okay? The very first step in the Schiff base hydrolysis, okay? The very first step is a nucleophilic attack on the carbonyl carbon, okay? So, again, you start with an amine, okay? But the amine nitrogen lone pair does a nucleophilic attack, okay? And as soon as you do the nucleophilic attack, this pi bond comes out and it's going to abstract a proton. Now, if you recall from our studies on enzymes, this reaction is reversible, so the sum of all the reactions in the total reversible reaction have to be reversible as well. So we have to indicate our double arrow here. Okay. Now, what you end up generating in this case is you end up generating this sort of tetrahedral intermediate. Okay. And so you have an alcohol here, and likewise here you're going to have nitrogen with 4 bonds. Okay. Now, initially what's going to happen is, assuming that you're in an aqueous environment, okay, what's going to happen is water is going to come in, or let's just say some base in general, because when we're talking about reaction mechanisms for, say, aldolase, there's going to be residues in the active site that are going to do these deprotonations. Okay, so the very first step after the nucleophilic attack is the base comes in and deprotonates here. Okay, and what that does is it forces this bond back up, these electrons back up onto the nitrogen. So what do we generate? Well, we generate oxygen with its hydrogen, right? And we generate N with H and R, right? So this is another intermediate state, okay? What happens next? Well, recall that what we did is we actually generated this conjugate acid form of our base, right? So the very next step in the mechanism, okay, that should be a lone pair. The very next step here is the hydroxyl group here is going to do a nucleophilic attack and abstract the proton from the base, and that forces the electrons back up onto the base. So what we end up generating is this other intermediate, but now we have a pretty good leaving group in the context of biochemistry. We have a protonated, we have an oxygen. It's effectively a water group, but it's oxygen with a positive charge, 2 protons. And now what we have is we have nitrogen with a proton, and we have this R group. Okay. Now the very next step of this mechanism, okay, what's going to happen is the lone pair from this nitrogen, okay, is going to kick in, reform a bond here, and this is going to force water off. So if we're running in this direction, at this point we end up losing water, okay? So what we end up generating is our protonated Schiff base, okay? So assuming we go by this particular mechanism, we're going to end up with a protonated Schiff base. And assuming that you're in an environment that has another base in it, you can end up being in equilibrium with the deprotonated version of the Schiff base. So in that case, you would end up with something that looks like this. Okay, you just have your generic R group there. Okay, this particular molecule is your imine, right? But that also implies that that's your Schiff base. Okay. Now, this is the sort of a general mechanism of Schiff base formation. Okay, if you follow this mechanism, pretty much all of the enzymes that are similar to aldolase will use this mechanism. Okay, so you have a nucleophilic attack by an amine, right? And then the amine, which will get a positive charge, by the way, can't forget our positive charge, will end up losing a proton. And then that same proton will be transferred to the oxygen, right? And then our electrons from the nitrogen will kick in, form the Schiff base, and kick off water. Okay, and of course, our Schiff base here is in equilibrium with our protonated Schiff base, right? Okay, so this is our mechanism of forming the Schiff base, and so this is the product we're generally looking at. Okay, now in enzymes like aldolase, we can also hydrolyze the Schiff base. So in the mechanism of aldolase, what we'll see is that you end up forming the Schiff base, okay, and then once you have the desired product that comes off of aldolase, then you hydrolyze off the Schiff base. So what we've seen up to this point is we've seen Schiff base formation, right? But we can also have subsequent Schiff base hydrolysis. Now, monoamine oxidase is an enzyme. We'll eventually look at the mechanism of it. The Schiff base formation of monoamine oxidase is a little bit different than the formation in the case of aldolase. In the case of aldolase, the original amine is a lysine residue of aldolase. It's different in monoamine oxidase, but the subsequent Schiff base hydrolysis is exactly the same mechanism. So for Schiff base hydrolysis, you're going to start with a molecule of water, right? And essentially, in the case of aldolase, the mechanism of Schiff base hydrolysis is exactly the reverse. It is the exact reverse of, it's the exact reverse of the Schiff base formation. Okay, so if you go back to our last step here, we deprotonated the Schiff base, right? Again, I keep forgetting this positive charge. So we deprotonate the Schiff base. So now what we end up having is we have our base over here with a proton on it. So whenever the water attacks here, this lone pair to this electrons to the nitrogen come up and they abstract the proton from the base. Okay, so what we end up generating is another intermediate. Okay, and what I want you to notice about this mechanism, it is the exact reverse of the Schiff base formation. Okay, so initially what we generate is this water, right? This water group basically. But the next step, what's going to happen is, if I can draw my arrows correctly, the next step is going to be another proton transfer. Okay, again, it's just the reverse of the Schiff base formation. So this base comes out, abstracts this proton from the oxygen, right? So what do we generate? Well, we end up generating this, right? So here's my nitrogen, hydrogen, R group. Now I have a hydroxyl group, right? And again, there's going to be another proton transfer. If I abstract the proton with that base, what happens? Well, that means I have the conjugate acid, right? And I have a lone pair on this nitrogen, which comes out and abstracts this proton again, okay? And then what does that generate? Well, that generates a very good leaving group, right? It generates a leaving group. So now I have 2 protons on this amine, right? And my R group. So what's going to happen now? Well, there's sort of 2 ways you can look at the next half of this next part of this mechanism. Okay, you can either sort of look at this in a concerted step or a stepwise mechanism. But suffice it to say, what's going to happen is you're going to have that base, right? You're going to have this base, and what's going to happen is either way, it's going to abstract this proton, right? But what's essentially going to happen is the bond between the hydrogen and the oxygen comes back and reforms a pi bond, and that effectively kicks this electron back up onto the nitrogen. So our final product, in any case, is going to be regenerating the ketone that we had. Okay, so again, all of these steps are equilibrium reactions. Okay, and one of the problems with organic chemistry is that there's a lot of material to learn and there's not enough time to do it. So unfortunately, for the sake of biochemistry, this is one of the chapters that usually gets left out just because there's not enough time. But again, Schiff-based chemistry is absolutely critical for understanding the mechanisms of biochemistry. So let's review the formation of the Schiff base. So amine does a nucleophilic attack, right? And then what we're basically doing here, if you think about it, we're switching the positive charge from the nitrogen to the oxygen, right? So in that respect, we're going to have how many proton transfers? We're going to have 2 proton transfers, right? One of them removes the proton from the nitrogen, and then it adds that same proton back onto the oxygen, right? Then what happens? Then we have this lone pair, right? It's going to reform a pi bond, right, to this. I guess you could call it the alpha carbon, right? It's not really the alpha carbon, but suffice it to say, it's going to reform a bond there, and then it's going to kick off water, right? And that forms what we call here. This is our protonated Schiff base, right? Now, the protonated Schiff base is in equilibrium with our non-protonated Schiff base, so we just simply refer to that as our Schiff base. Now, if we want to reverse the Schiff base formation, that's just going to be our Schiff base hydrolysis. And so in the mechanism of aldolase, what we'll see when we actually look at the actual reaction is that, remember that it reacts with fructose 1,6-bisphosphate, right? So the enzyme is actually more correctly called fructose bisphosphate aldolase, okay? But effectively what's going to happen is you're going to form the Schiff base, and then you're going to subsequently hydrolyze off one of the products, okay? So in the general mechanism, water is going to come in, and it's going to nucleophilically attack this carbon right here. That forces the electrons to the nitrogen to go abstract a proton from our base, right? And just remember that base that we're talking about, that's just an amino acid residue in the active site, right? Okay. So those are going to be your generally what we're talking about when we're saying a lot of times, I don't know this for fact with aldolase, I'd have to look it up, but usually when we're talking about acid-base catalysis, common residues are glutamate, aspartate, histidine, sometimes tyrosine is used for that, but generally we're just talking about an acid-base catalytic residue, okay? So water attacks, you're going to have a proton transfer. And effectively, remember what we did up here in the Schiff base formation. We effectively switched the positive charge from the nitrogen to the oxygen, right? So here it started on the nitrogen, it's going to the oxygen. So what do you think we're going to do in the reverse? Right, we're just flipping the positive charge from the oxygen ultimately to the nitrogen, right? And again, I keep forgetting this should be a positive charge, right? So we're flipping it from the oxygen to the nitrogen, right? And so it really is the exact reverse of Schiff base formation. So again, base comes in, abstracts this proton, right? These electrons kick in to form a pi bond, and it kicks off your amine. So not only do we end up generating our ketone again, but we end up generating the product, which is just NH2R, right? Just a generic R group. And if you remember back how we started, that's what we started with. We started with RNH2. Okay, so again, there are a lot of enzymes in biochemistry that utilize Schiff base formation and Schiff base hydrolysis. In fact, if you've taken biology classes and they talk about things like methylation and demethylation of DNA, the methylation does not use this, but the demethylation uses a mechanism that's very similar to this. Now, in terms of the initial Schiff base formation and demethylation, it's very similar to monoamine oxidase's Schiff base formation. But the Schiff base hydrolysis in all enzymes is exactly the same mechanism. So really, probably the most important thing from this mechanism to understand is the Schiff base hydrolysis. It's the same for demethylases, the same for monoamine oxidases, and it's of course the same for aldolases, okay, which we'll see in glycolysis. The only enzyme out of those that you'll typically see in biochemistry, one is aldolase. But again, it's just important to see and understand Schiff bases just because they're often left out of organic chemistry. So I hope this video helped you get a little bit of an intuition on Schiff base formation and hydrolysis. In the next video, what we'll do is we'll actually look at the other mechanism of Schiff base formation, and that's going to be something that is utilized by an enzyme like monoamine oxidase. See you in the next video.